Good morning, everyone. Today we are going to start our class from today. So, before going to start the class, let's have a brief discussion about the last two classes, what we have learned about the magnetic field, so that we can continue our next topics. So, we have studied about the magnetostatics, the biot law, and the magnetic field or the magnetic field intensity for an infinite long current carrying conductor. So let's have a brief discussion about it. Let's start with the magnetostatics. So what do you mean by the magnetostatics? So magnetostatics is nothing but it is a study of a steady magnetic field. So magnetostatics is nothing but the study of a steady magnetic field. What do you mean by this steady magnetic field? So what do you mean by this magnetic field? When the magnetic field will be produced, we all know that the charges are present. If the charges are present, then there exists a electric field. Even if there is no motion in the charges, if there exists a charges, if the charges are even at rest position, there exists a electric field. Similarly, if there is a movement in the charges, if there is a movement in the charges, then there exists a magnetic field. So we are talking about the movement in the charges. So if the charges are moving, if there is a motion in these charges, then there exists some magnetic field. So how do these charges move? How can be there is a motion in the charges? So if we consider a conductor, let us suppose we are considering a conductor. For a conductor, we are giving a supply. Let us consider a DC supply. So whenever we have given a supply, DC supply to a conductor, so due to this positive plate, the charges, the electrons gets attracted toward this place, so there exists the movement of these charges. So whenever a steady current, that is steady current, steady supply, that is a constant supply is given to a conductor means there exists some charges. Conductor is nothing but a material consisting of the charges. So this conductor, whenever a DC supply is given to this conductor, there exists a movement of the charges. So since the supply is a constant supply, the steady supply, we are calling it as a steady, and the charges are moving, we are calling it as a steady magnetic field. So the steady magnetic field is produced whenever supply is given to a conductor. So whenever a supply is given to a conductor, there exists a movement of charges. So if the charges are moving, we will be calling it as a current. So we are calling it as a current carrying conductor. So whenever there is a current carrying conductor, there exists a magnetic field. This is about the magnetic field. Since we are giving a supply of a constant supply, a steady supply, we are calling it as a steady magnetic field. And this, the behavior of this steady magnetic field is nothing but it is called as a magnetostatics. I think up to now it is clear to everyone. Okay, so we have clearly known about the magnetic field, how the magnetic field is produced. So whenever there is a field produced, how much field it has been produced, the first point, and what is the strength of the field we have to determine. So the magnetic field or the magnetic field strength, the magnetic field strength, that is the strength of the magnetic field, or it is also called as an intensity. So this magnetic field or the magnetic field intensity can be determined by using a law which is called as biot savarts law. So this is called as biot savarts law. So the biot savarts law explains the magnetic field intensity at a particular point, or how much magnetic field is produced, or how much the strength of the magnetic field is there at a particular point, can be known by using a law which is called as a biot savarts law. So what is this biot savarts law? Let us think. So the magnetic field is represented with letter B, the magnetic field intensity is represented with letter H. There is a common relation between B and H if you have studied in the magnetic field circuits, So we know that relation B is equal to mu into H. B is equal to mu into H. Where mu is called the proportionality constant, the permeability. So again we'll be having mu is equal to mu naught into mu r. This is absolute permeability and this is the relative permeability. Always this value will be 4 pi into 10 power minus 7 and mu r will be 1 for some space and it will be having other values for depending upon the medium or the material. So this is the relation. So B is represented for the magnetic field and H is represented for the strength of this magnetic field. So let us, this biot law, either we can determine the magnetic field using this biot law or either the magnetic field intensity. Anything we can consider. If you are using magnetic field, so you can write it as in terms of mu into H. If you are using H, directly you can write, and from that you can determine B by mu. Anything you can cover. So let us consider the magnetic field intensity. So this magnetic field, here we are considering about the magnetic field intensity. So the magnetic field intensity at any point, according to Biot's law, states that it is directly proportional to the current flowing through that current carrying conductor. It is directly proportional to the length of that current carrying conductor and is directly proportional to the sine theta and is inversely proportional to the square of the distance. So the Biot's law states that the magnetic field or the magnetic field intensity is directly proportional to the current which is carried by the conductor, the length of the conductor, sine theta, where theta is the angle. We'll be considering what is that theta and what is that angle, why we are considering only sine theta. So just now remember that it is directly proportional to sine theta, and the next one is it is inversely proportional to the square of the distance. So from this we can write that the magnetic field intensity, let dH, if you are writing, it is directly proportional to I dl sine theta by r square, and from this you can write it as dH is equal to I k, proportionality constant, k I dl sine theta by r square, where k is called as a proportionality constant which value is given by 1 by 4 pi. So dH, if you are writing dB, then write it as mu into H, so you can write it as k value as mu by 4 pi. This is the constant k for B and this is the constant k for H. Can represent, if you are writing here dH, then write the k value as 1 by 4 pi. If you are writing here dB, write the value of k as mu by 4 pi. So from this it is clear that magnetic field intensity dH is equal to k value, we have written it as 1 by 4 pi, so you can write it as I dl sine theta by 4 pi into r square. So dH is equal to I dl sine theta by 4 by r square. Okay, so but we know that the magnetic field or the magnetic field intensity will be having a direction. So since we have to represent that one in a vector quantity, let us consider a vector quantity. So here we know that if you are considering a current carrying conductor, let us suppose this is a current carrying conductor, and let us think that here is a point where you have to find out the magnetic field intensity. So total length of the conductor, we are considering a differential length dl. So due to this, the produced magnetic field intensity will be differential magnetic field dH. So let us consider the distance between these 2 points will be r. Here there will be an angle theta. So here theta is the angle between the differential element differential length and the distance between these 2 points. So in order to make these magnetic field intensity to represent in a vector quantity, so we should require 2 vector quantities. So this is a distance vector, we know that, and the differential length is a scalar. We have to make this one into a vector quantity. So in order to make this vector quantity, you should have a direction for this. The direction of this differential length is nothing but the current flowing through this conductor. So the direction of the current is nothing but it represents the length direction. So from this we can write it as dh, that is we are representing in a vector quantity. You can write it as I dl bar. What is this I dl bar represents? I dl bar represents the differential length of that current carrying conductor with its direction of I. So I dl bar represents the differential length direction. The direction of this differential length is nothing but the current direction, so we are taking it as I dl bar. Next we are considering a vector quantity R. So before going to this, let us multiply both numerator and denominator of this expression with R. In this expression, both numerator and denominator is multiplied with R. Then you will be getting R and R. So from this, you will be getting an expression of I dl R sin theta by 4 pi R cube. Now, in order to represent this one in terms of a vector quantity, now we are placing here, we are representing with vector quantity as I dl bar, and R is the distance between these 2 points. Let us represent this with the vector quantity, so we are writing it as R bar by 4 pi R cube. What is this I dl cross R bar? The cross product of 2 vectors. You can write it as cross product of 2 vectors. A cross B is equal to mod A mod B sin theta, where theta is the angle between A and B. Here also we are telling that the theta is the angle between dl and R, and you are representing the differential length and R as a vector quantity. So the total expression of this can be written as I dl cross R by 4 pi R cube. And still we can write this expression as I dl bar cross R bar by 4 pi R cube. We can split R cube into R square into R. So if you observe here, this R bar by R represents the vector divided by its magnitude. So we can write it this one as I dl cross AR by 4 pi R square. This is the magnetic field intensity of at a point due to a current carrying conductor. The magnetic field intensity due to a current